Well, hello there, everybody. Welcome back to another exciting physics lecture. Today, we're going to move on from our circles intro to circles with some forces. Not a real tough day, so anyway, let's jump to it and see what happens. A couple things real quick. Remember that when we're going in circles, the acceleration and the force both point towards the center of the circle. All right. Think of something spinning around with a string, and the string can only really pull into the middle. Next thing, we have a name for that force, and actually that acceleration as well. The force that points towards the center of a circle is centripetal force, not centrifugal force. Okay, centripetal. You should get comfortable with that word. That's a word we're going to use a fair amount. All right, centripetal force, a force that points to the center of a circle. And centripetal acceleration also points towards the center of a circle. So let's have a look. If we look over here at our mass that's going in a circle, all right, we have the radius of the circle and the velocity, which is always perpendicular to the radius or tangent to the circle. We have our mass that we make as a dot, and then we have our F with a little c for centripetal force. Now, that centripetal force can come from a lot of places. It can in some cases be a string or ropes or friction or whatever. But to make things go in a circle, it always points to the middle of the circle, and we call it centripetal acceleration. Also, or centripetal force and centripetal acceleration as well. So if we look at our examples here, the physics teacher spinning the ball with a string, it's a force of tension on the string, but it's also the centripetal force. The car, there's friction with the road, and so the frictional force in this case is also this centripetal force. Okay? So hopefully that doesn't get too confusing. Same with the bottom picture there, the amusement park ride. Those chains are in tension, so there's a tension force because they're like ropes, but it's also centripetal force. All right, for this video, we're just going to start with circles that are horizontal. So the guy spinning something around his head in a horizontal plane, a car going around a circle, going around a curve. We also have turntables things. Now this is a picture of something called a record. You may have heard of them. You might want to ask your parents about them. But it's on a turntable, so a table that can spin around. All right. All of these are something that's going in a circle that's horizontal. All right. Let's talk about cars for a minute. Okay. Here's a picture of a car going around in a circle, and the force is towards the center. All right. The force is being provided by the wheels against the pavement. Let's draw. I'm going to draw some velocity vectors. There's our velocity vector. There's one. All right, and there's another one. Okay. So our velocity may not be changing magnitude or length, but it's changing direction. So this is a kind of a confusing point. A lot of folks say, well, there has to be centrifugal force on me. I'm being pushed out of the circle when I'm in a car. All right? So let's imagine something. Okay? Let's imagine you're going along in your car straight. So this first picture here, in our first situation, let's pretend there was no curve before that. You're driving along straight, so you're sitting just fine in your car. All right? Let's say you're the passenger. So the driver takes the wheel and turns it. and starts going towards the second picture, the middle picture there. Well, what you want to do, if there's no forces on you, is to keep going in a straight line. You'd like to keep going with a velocity v, but the car stops you from doing that. So the car takes you and pushes on you, in this case, on your right shoulder, and pushes you to the left with the centripetal force. Oh, I almost said it wrong. Centripetal force going in to make you change direction. You are not trying to go out of the circle. You're trying to go in a straight line. The car doesn't let you keep going in a straight line. It keeps changing your direction by pushing on your right shoulder, so you go in a circle towards the left. Okay, so this is a big idea. We think we're getting thrown out from the circle, from the corner, but we're not. We're just trying to go in a straight line. I want you to try this. So really pay attention next time you're in a car. Be a passenger, and when you go around a corner, look and see what's going on. You're actually just trying to keep doing what you're doing, which is go in a straight line. As soon as the driver turns, you actually get pushed into a circle. All right? Try it. It's actually kind of cool. If you really pay attention, you can see that's really what's going on. Okay? So there's no such thing as centrifugal force. There is nothing pushing you out. The only thing that's actually happening is the car is pushing you in, and you're trying to keep going in a straight line, but the car does not let you. All right? Hard idea. This is a tricky one. Don't even say centrifugal force. Does not exist. Okay? So we'll practice that in class some. That's a tough idea. Alrighty, so there's cars and corners. Let's move on. We get to do just a touch of easy math here. First of all, we're going to start with that centripetal acceleration, that acceleration towards the center of a circle. Now notice how we're going to write it. We're going to write it A with a little c there. And here's what I remember. I think, oh, that's A for circles, and it points to the middle. Okay, and it's centripetal. All right, and it's v squared over r. All we do is we take that and we plug it into Newton's second law, into the sum of the forces equals ma. So for A, all you do is you plug in v squared over r, and you get m times v squared over r, and you can start working with the forces in circular motion. All right? Pretty straightforward. That's as bad as we're going to get with the math today. Nice easy math day, excuse me. Alrighty. Let me tell you one thing just to be careful of. Here we've got a box on a big turntable. A blue box on a yellow turntable. Alright? Let's just look at the right picture now. I'm sorry, the left picture. I just lied to you. So I want you to just focus on this picture for a minute. Let's draw the centripetal force on the box. All right. So the centripetal force on the box goes towards the center, and it's F with a C. Now, in this case, this centripetal force is also the static friction force. All right, and you could use either one when we're solving this problem. The static friction force is what's making the box go in a circle, and we call that the centripetal force. Okay? All righty, now, real quick, notice something. We can't draw a free body diagram of this because we're looking down on the top of it. So, let's look at things from the side, like right here. And let's make the turntable spin this way. So right at this point on the picture on the right, the box is going out. Okay? The box is coming out towards us. Then it's going to go around. When it gets to the other side, it's going to be going back in. But let's take that centripetal force that we drew and let's draw it again on the box. There's our centripetal force, which is our force of static friction in this case. All right? Now, it's pointing towards the center. Let's take one more step, and I want to draw an FBD of that box. Okay? Here we go. There's force due to gravity, which equals mg. There's my normal force, which is going to balance in this case because it's not moving up or down, so that's also going to be mg. But check this out. Here we go. Centripetal force. Okay? Force of friction. Notice something. The forces are not going to balance. In the x direction, in the crossways direction, the only force acting on this is the centripetal force. All right? So it looks like the box should fly off towards the right. Well, look at it. It is kind of going to do that. It's going to move to the right because the thing is spinning. So it's gonna go that direction. Since it's moving out towards us, it's also gonna curve at the same time. This gets tricky because you got to think in 3 dimensions. The box is moving out towards us, but as it moves, it's gonna curve as well. So that centripetal force is gonna make the box move to the right. All right? Now, that's a tough idea, and sometimes kids have trouble with these pictures when they draw them. But really, a little while later, the box is going to be more to the right because of the spin of the turntable that it's on, the yellow disc that it's on. All right? So don't get freaked out when your free body diagrams don't balance the forces. Don't have equilibrium. All right? The sum of the forces does not equal 0. All right, in the crossways direction, sum of the forces equals m times the centripetal acceleration. Okay, so sum of the forces in the x direction equals m times the centripetal acceleration. And the only force we have in the x direction is the centripetal force equals m times the centripetal acceleration. Okay? We don't get to set things equal to 0. Alrighty, enough of that. Here's your video lecture problem. Okay, basically it's the same problem. I want you to have a look real quick down at number 4. Just make sure you're okay with the centripetal force equaling the force of static friction. Okay, the Fc, centripetal force, equals the force of static friction. All right, let's see what you can do with this. Come and ask me tomorrow if you have trouble. Have an awesome evening. Good night.